Hi everyone, welcome to this lecture. So in this lecture, we will learn about the kernel trick in SVM. That is, we will see how we can use a kernel with support vector machine in order to improve the performance of a support vector machine, or in order to use the support vector machine for a more challenging data set. So till now in this section, we have learned about this kind of a data set which is linearly separable. So this is a 2D data with dimension along x1 and x2. And we can easily separate these two classes with the help of a straight line. Since these classes can be separated with a straight line, therefore this data is linearly separable in 2D. On the other hand, here is a data set which cannot be linearly separable in 2D. This data set is also a 2D data set with dimensions along x1 and x2. So we can see that we cannot draw a straight line that can separate these two classes. So in order to use support vector machine here in that kind of a data which is not linearly separable, we need a kernel. So the kernel trick will help us in order to perform the classification using a support vector machine for the data set which is not linearly separable. So for this kind of data set, which is a non-linear data set, we need this kind of a classifier. So this kind of a classifier will only be available only in support vector machine when we use a kernel trick with support vector machine. Okay, let's start kernel trick in support vector machine from the simplest example, that is in 1D. So how kernel works and how kernel make the data linearly separable. So this is our data. So this data is in 1D, that is it has only one dimension which is along x1. So we can see that this data is also not linearly separable in 1D because there are two labels here. This is our blue label and this is our red label. So we cannot draw any straight line that can separate these two labels because they are spread in a way that we cannot draw a straight line in order to perform the classification for this 1D data. So what we will do with the kernel trick and what kernel will do, basically when we apply a kernel on this data, so here is the kernel trick. It will project it into the higher dimension. So we can see that this is x1. And when we perform x1 square, now we have two t data, that is one along the x1 and one along the another x1, that is it is the x square data or x1 square data. So when we perform the square of this 1D data, we get this shape. Now we can see that in that shape, it is easy to perform the linear classification. That is, here we can draw a straight line in order to separate this blue class from the red class. So what kernel did with this data? So the kernel has projected the data to a higher dimension to make it a linearly classified data. So that data was in low dimension, that is in 1D. When we apply a kernel, it projects the data into a higher dimension. And now this data, which was not linearly separable in 1D or in the original form, it is now linearly separable using a kernel trick. So we can see that this is now our decision boundary, and now this data is linearly separable in 2D, which was not linearly separable in 1D. Now look at this data set. If we want to perform the linear classification of this data, so this data is in 2D and it is not linearly separable in 2D. So what we will do, we will use a kernel trick and we will project the data from 2D to 3D. And we will see when we project the data to a higher dimension, that is from 2D to 3D, it will be linearly classified. So here is the trick. This is our data, which is not linearly separable in 2D. When we project this data into 3D, this is the 3D representation of this data. Here we have three dimensions, that is dimension along x1, dimension along x2, and dimension along x3. So we can see that if we projected a 2D data into a 3D data, it is now linearly separable. So this is our decision plane now. Keep in mind, we are in 3D now. So our decision boundary or a decision plane will be 2D now. So the dimension of a decision boundary or a decision plane is always one less than the dimension of the data. If the data is 2D, then we draw a straight line. So if the data is 2D, the dimension of the straight line or the decision boundary is 1D. On the other hand, when data is projected to 3D, in that case, our decision boundary and our decision plane will not be a straight line of 1D, but it is a decision plane of 2D. So the dimension of a decision plane or a decision boundary is always one less than the dimension of the data. If you have a three-dimensional data, then the dimension of a decision plane or a decision boundary is 2D. So we have seen that that data was 2D initially, and it was not linearly separable in 2D. We used a kernel trick. We project the data to a higher dimension, that is, we transform the data from 2D to 3D. And in 3D, it is a linearly separable data, and we separate it by a linear decision plane here. So it is linearly separable in 3D. So there are many kernels which we can use with support vector machine. So the famous kernel or the kernel which performs well as compared to other kernel is the Gaussian radial basis function, or in short, we can say RBF kernel. So this is our radial basis function or RBF kernel, and this is the equation of the radial basis function. So this kernel is the Gaussian kernel, and this is the shape of the Gaussian kernel. And we can see that in order to find this, if you see this equation, there is a mean. We calculate the mean of the data. We subtract the mean from each sample of the data, and then we divide with the sigma square. So in that case, we square the data and we project the data to a higher dimension using this RBF kernel. So in this lecture, we learn about the kernel trick used in support vector machine. And we have seen that by using a kernel, we have improved the performance of support vector machine. And now support vector machine can be used to perform classification in a more challenging data. That is, if we have a data which is not linearly separable in any dimension, that is in 1D or 2D, we project the data to a higher dimension using the kernel, and that data becomes a linearly separable data in a higher dimension. So I hope you understood the importance of a kernel in support vector machine. Thanks for listening, and I will see you in the next lecture.